Yeah, so thanks so much, everyone, for coming, and to the organisers for inviting me to talk. It's a great pleasure to be here. Yeah, so, and yeah, I guess, commiserations to everyone on the newsletter today, and let's just soldier on with the maths and pretend that everything's fine. So today I want to try and talk about some kind of generalized, oh, thank you. So I want to talk about some kind of generalized modularity properties that and how they relate to Borel resummation. But I was inspired in the last talk to give you a bit more of maybe the motivation from physics. So in particular, the kind of series that I'm interested in resumming come from perturbative Chern-Simons theory. So perturbative Chern-Simons is given as usual by some kind of exponential integral. So here I integrate over some space of connection. So M is some 3 manifolds. These are some space of, say, SU2 connections, for example. For me, it's always going to be something like SU2. And then here's the gauge group. And so these are connections on the 3 manifold. And we're going to take some kind of integral over these connections, weighted by the usual e to the action. So here, this Chern-Simons functional. Yeah, okay, let's do it like this. Okay, so where this Chern-Simons is some kind of local functional defined on the 3 manifold. So in particular, we integrate the 3 manifold over a trace of some connect. So we take the connection 1 form associated to A, and we construct the following 3 form and integrate over the 3 manifold. So here we haven't required any metric or anything on the 3 manifold, and this is just some kind of topological quantity. And so here there is one issue related to this definition. And so this was all studied by Witten trying to interpret invariants that Jones constructed in the late 80s. And so there's one issue here, which is that this functional is not actually gauge invariant. So this is only an element of the complex numbers modulo 2 pi I squared. So in particular, if we want this integral to make sense at all, we have some sort of quantization condition on h bar. So we have h bar is an element of, let's say, 1 on, what do I want? 2 pi z, I think. Okay. But so you can, at least if you believe that this path integral makes sense, you should have a nice invariant for each h here. But this kind of integral is some kind of infinite dimensional version. Some kind of infinite dimensional exponential integral. So an exponential integral is essentially this. You integrate over some function over some space. And so normally we would consider these over some sort of finite dimensional spaces. And the point is that these integrals have very nice, we know how to compute their asymptotics in finite dimensions. And so what you do in perturbative quantum field theory is you basically imagine you could try and do these computations in the infinite dimensional setting and force yourself to make sense of it. And so what we expect from these kind of integrals is we expect some perturbative series in h bar. And they should be dominated by critical points of this functional. So here, so coming from critical points of this Chern-Simons functional, which are equivalent to flat connections. Okay. But so how do you, in practice, in a real world example, how do you, like in a finite dimensional example, how do you recover this perturbative series? I mean, you take a contour which you deform close to a critical point. But so here I have a little bit of difficulty with respect to this H bar because I have this quantization condition. And so what one should really do in this case is take some kind of, instead of taking these SU2 connections, mod gauge, so we want to replace this space by some left-fit stimulus. So some kind of half-dimensional cycles in this infinite dimensional space. And they should be centered around these critical points. And so what we expect, so we should lift this function here to some coupling of connections which keeps track of this H bar, like you lift the logarithm on the complex numbers as some locally defined function. You can lift it to its Riemann surface. So we try and do the same thing here. Then we take thimbles there. And so what we expect is to get not only asymptotic series, but we expect analytic functions in H bar. So now H bar doesn't, maybe H bar lives in some half plane, but it doesn't have this quantization condition. With the asymptotics we'd expect from these integrals with associated asymptotics. Okay, so to construct this analytic function from this description is quite difficult. And I don't know how to do it. But there's sort of a way that we can approach these problems using basically the locality of this kind of integral. We can reduce this infinite dimensional integral down to some finite dimensional integral. And these are the things that we're going to address. And these can be mathematically defined, and we're going to analyze their properties. So what we'll do today is so we'll look at a finite. So we'll look at a finite dimensional analog of the integral. Or finite dimensional, let's say, model. And we'll tackle that. And what turns out, so it turns out these functions come from some kind of modularity property. So, and in this case, come from some quantum modular forms. So these are some kind of functions that try to satisfy symmetry, but the symmetry fails. And the failure of that symmetry is exactly encapsulated by these functions that we would like to understand. Okay. So this is what I want to aim towards. And so this is a little bit of the physics motivation. But now I want to get straight into modular form. So are there any questions about this? Okay. Great. So yeah, so I want to start with classical modular forms. So not these sort of fancy quantum ones. And so these classical modular forms will be related to very special and simple three manifolds. So in particular, non-hyperbolic three manifolds will be related to these classical modular forms. And the classical here, sorry, so the classical and quantum here, really you shouldn't think of some quantization. This is just horrible terminology, so I'm very sorry for this, but yeah, don't be confused by that. Okay, but so these classical modular forms, oh yes. Yeah, exactly. So quantum is somehow coming from hyperbolic, and classical is sort of non-hyperbolic. Yeah, so classical modular forms are holomorphic functions that satisfy a large set of symmetries. So in particular, if we have, so throughout the talk, it's going to be something like this: gamma equals ABCD in SL2Z. So of course, these 2x2 matrices act on the upper half plane by Mobius transformations. So the variable in the upper half plane I'm going to take is always going to be this tau. Okay. And so classical modular forms of weight k would satisfy some functional equation like this. So if I act by Mobius transformations on the argument, I get back essentially the original function, but slightly twisted. So here, this is for weight k. Okay. And so, at the start, I said I was interested in understanding some kind of asymptotic series. And so here, this functional equation actually gives me a complete understanding of the asymptotics of these functions as I send tau to a rational. Tau a priori is in the upper half plane, but I can now understand the asymptotics using this equation. So in particular, if the first sort of property that this implies is that this guy is invariant under integer shifts. So this therefore implies that I can write f as a Fourier series. So this is plus, to get a low bounty, you have to plus some growth conditions. But don't worry about it, some technical. But so I can write it as some kind of Q series here, where Q is e to the 2 pi I tau. Okay. And then I can use this transformation property to basically understand what happens as the argument of f approaches a rational number. So in particular, I have a tau plus b on tau plus d. As I send tau to I infinity, then this will approach a divided by c. And then from this, I can basically, I have a complete description of the asymptotics. It's going to be c tau plus d, okay? And then there's going to be one leading term, because here, of course, as tau tends to I infinity, there's only one of these terms, q, that will contribute asymptotically. All of the others will be subleading. And so therefore, I see that the asymptotics of this thing is just given by this first constant and q to that first power. So this is a very, so the asymptotics of modular forms are very, very well behaved. So in particular, these are essentially convergent. Okay, you have this kind of exponential singularity, but it's just as a series itself would make sense. Sorry, was there a question? Yes. Yeah. Yeah, yeah, exactly. So tau is related to h bar in this case. So there's going to be some relation, like tau is something like, what do I want? I think tau is going to infinity, so I think I want like this, something like this.
So why is that modular if you have a model of this integral? Why is it modular?
Why would have this? Yeah, so it's not obvious from, yeah, how to say? So there's a few things you can say, I think, from the path integral. For tau in the upper half plane, yeah, so let me think. Yeah, so basically you can do something like, if you think of this thimble, you can, if you look at the original integral and then you decompose it and you sort of push the thimble to infinity, I think you catch different contributions from lifts of various connections. And sort of when you interpret the integral that you're trying to push away, I mean, it's sort of a bit vague because in this infinite dimensional setting, but sort of by deforming the contour, you can kind of see that the integral should relate sort of large h bar and low h bar in some way. You should be able to decompose it in two ways. But that's very vague. But there's physics literature on this like work of Marino and Prutrov and Gukov, and people play with this stuff. So the full thing will turn out to be related to essentially this. So the full thing will sort of be some kind of failure of modularity. So so you shouldn't think that this f will be the path integral. The path integral will be related to something like this. Yeah. Mm-hmm. No. So the tau here is sort of in relation to the h bar, not some parameter on the manifold. So h bar is kind of independent of the manifold. Okay.
About the tau. So
yeah, sure.
Purely imaginary?
No, just imagine imaginary part greater than, so upper half plane.
So the exponential is to binary.
Yeah.
What happens in the semi-classical unit?
Yeah, so here it's yeah, maybe there's plus minus. Basically, so this Q here would look like something like 1 on h bar, I guess. Maybe did I do something wrong? Yeah, okay, there's some 2 pi I don't know, plus minus. Yeah. Yeah. Okay, but yeah, so this is sort of this is a classical modular form on the full modular group. So here I've taken all possible things here, but you can take sort of some more interesting examples. So for example, you can consider these famous Ramanujan functions. And so these are given by some very nice formulas. So they're some kind of Q hypergeometric functions. So here you can describe them as follows. So here this thing here is the Q Pochhammer symbol. Okay, so from 0 to k minus 1. Okay, so this is the first one. It has this sort of famous identity here, which basically says that this has a product formula. So this turns out to be equivalent to a product n greater than 0, and then some congruence condition mod 5, so plus minus of the following form. And this has its friend, which is given by almost the same formulae. So here I just shift by some linear factor. And it also has a nice product expansion now for the other congruence classes. Mod 5. So these two identities are these Rogers-Ramanujan identities. And the interesting thing about, why these identities are interesting is that something with this kind of product expansion, it's well known how to understand its modularity properties. So here, this function here, it's not clear at all that this would be some kind of modular form, but these guys are sort of known functions that would be related to modular form. So if we put these together in some kind of vector, then this is some kind of vector valued, or this is a vector valued modular form. Okay. And so it satisfies, so as sort of a consequence of these modularity properties, this guy satisfies a transformation sort of as follows. So if I act by tau, so here I sort of abuse the notation and write, a function f of q that's modular is also a function of tau. So if there's any confusion, just ask me, but it's generally clear. So if I act by an element of SL2Z, then this guy is given simply by a 2x2 matrix, which is essentially a representation. So this row is a representation so this is a representation of SL2Z, and it's generated by the following matrices. So this guy is given by, well, you can all compute this. So it's a 60th root of unity here. So you see this is invariant as tau gets shifted by tau plus 1. But here we get the inverse of the 60th root of unity, and similarly here. Okay, and then the other generator of the modular group is, of course, this one. And this has got some particular form. So I'll give it to you just for fun, because I like numbers. So it's got some entries in the field square root of 5. You can write them as follows. I hope it's readable for everyone over here. Sine pi over 5 and sine minus sine 2 pi over 5. Okay. So this gives you some representation. Very good. And so now we get slightly more interesting asymptotic behavior. So now that we went from this sort of scalar valued modular form to a vector valued thing, we can still look at the asymptotics, and we see it really depends now on what rational number we approach. So yeah, for example, if I take the asymptotics as tau tends to infinity, or I infinity, whatever, then yeah, of course, this guy is just going to be given simply by the first row of this matrix with the q to the minus the 60th. But then on the other hand, if I took, so if I use those generators and I took, for example, the asymptotics as tau tends to I infinity here, so we approach minus a fifth, then this guy would look like theta over 12th, and then we get sort of two different exponential behaviors here. Okay. But so already with this vector valued modular form, we see that when we look at these asymptotics, there's sort of some kind of dominating terms and then some sub-dominating, sub-leading terms. And we want to understand how to package these all together. Okay, let's see how we're going. Slowly but surely. So are there any questions on this? I think I'm slowly nodding this, but okay. Yeah, so then the sort of next natural class of functions that comes up has this nice history, which I mentioned in the abstract. So just before Ramanujan died, he wrote his famous last letter to Hardy, where he introduced, or he gave basically a list of examples of something that he called mock modular forms. And it was basically almost 100 years where people had no idea the structure these functions satisfy. Ramanujan gave a very nice list of functions and people studied them lots, like Watson made a lot of progress. But then in sort of the early 2000s, with Zwegers' PhD thesis, there's sort of the automorphic properties or these symmetry properties of these functions were much better understood. But that's not the perspective I want to take today. So I want to give you a definition, like I gave you this very quick definition of or part of the definition of a classical modular form. But I'll sort of give you the flavor of these mock modular forms as Ramanujan saw them. So we already saw that these modular forms have extremely nice asymptotics. So it's really some number, maybe some power of essentially tau, and then some exponential term. So this is extremely, extremely nice. And Ramanujan saw that these mock modular forms satisfied a very similar thing. So here, the example that I want to give you is related to just as a slight variation of this function here. So Ramanujan considered the following example. So it's essentially the same formula. However, I just want to check that I got the right one. Yeah. You just add a little sign in this Pockhammer symbol here. So instead of having 1 minus q squared, you have 1 plus q squared. And so what Ramanujan realized about this function is this has asymptotics like a modular form. Okay. Okay, yeah, so maybe I'll give it to you in this example. I'll just give you a example. Let's see. What do I want? So here I want to actually take the vector like I did here with this little g. So I'm going to add here the vector. I'm going to put q to the minus the 60th again. And here q to the 11 over 60, but plus k in the same way. Okay, so this is some vector valued q series. And so what you find if you look at the asymptotics, say, of the first entry of this. So let's take the first entry of this, and I want to do it when the argument approaches a half. So what you observe is this kind of leading order behavior. So there's some constant here. I won't give it to you because even I'm getting sick of the constants. So there's some constant. Okay, you have this thing, and then you have exactly the same behavior we saw before. So here you get this q to the minus the 60th. But of course, this, as I said, is convergent. I mean, there's some constant, okay, this square root, whatever. And I have this exponential here. Okay, it doesn't make sense when tau is infinity, but I can evaluate it at finite tau. So I can subtract this from the left-hand side. So this looks like a modular form, weight half. But what you find is if you remove that, you get some interesting series. So here I get, okay, just because I did some stupid thing in my normalization, I have this, you have the series coming from this guy. And then what you find is some series appearing with rational coefficients, of some minus 2. 2 tau plus 1, da, da, da. So this guy is some series, let's call it P1 of x. And so something like 2 plus 4x plus 36x squared, blah, blah, blah. Okay, not all integers, just the first few. And now, if it was, I mean, in this case, we had some nice asymptotics that was even convergent, so I could subtract it. But now I have an issue. This series is no longer convergent. It's factorially divergent. So the terms of this series you can show grow like, you know, the coefficient of x to the k grows like k factorial. So to be very precise, also to be more precise to the answer to the question I gave before, these kind of series show up as the perturbative series around the trivial flat connection for these Chern-Simons path integrals for non-hyperbolic manifolds. So if you take the trivial flat connection and you do perturbative series around it, you get these kind of series coming up. This is probably even an example for some free manifold, but I wouldn't know it off the top of my head, some lens space. Okay, and then this guy, a differential equation, it could be implied from the mock modularity, but what is sort of very obvious that it satisfies is it's part of a family of series that satisfy a Q difference equation. So if you replace, so if X, so maybe I should stick to sort of vaguely the notation that I had. So maybe X should be H bar. And so my Q should have, you know, been something like E of H bar, but it's not because I swap things anyway, because this modularity switches things around. But there's an infinite list of these guys basically indexed by the linear shift I put here. And so I could have kept adding here. So I could have had, you know, 2K, 3K, blah, blah, blah. And there's only 2 of these are independent. So the rest satisfy a nice recursion here. So because they come from these Q-over geometric functions, they satisfy sort of naturally Q difference equations. But there might be some differential equation as well, but it's maybe less canonical. It's a bit more, I haven't seen it in any applications for this at least. But yeah, an interesting question. So then, yeah, as I said, I want to turn these kind of series into analytic functions. And so what Zwegers showed is that, so this guy isn't a modular form because of this. But what Zwegers showed is that the sort of failure of modularity has better analytic properties. And so here, let's just essentially just ignore this term for a moment. So we have this phi that's floating around. But if this was a modular form, I could keep subtracting off my terms and I'd get my full Q series expansion. I could discover it all from the asymptotics. And so let's just ignore this term for now. And if you essentially take the difference that would be 0 if it was a modular form, you see something quite remarkable happen. So in this case, you take this thing here, and then you get this representation that dictates these constants that I ignored. And so you have 2 constants. And what you do is you subtract this term, and then you get the other constant for the other part of the matrix. How? Okay, so I don't know, this is a different constant. Of course, this should all be multiplied by square root theta plus 1. Okay. So what you find, so work of Zwegers implies that this guy, so it's sort of a bit of work. I mean, it's not completely trivial, but you can show that this guy is equal to the so-called Borel resummation of the series phi 1. And so what does this mean? So for me, what it's sort of going to mean today so basically this means that this combination here, I don't know. So this means that this function has asymptotics equal to this phi 1 series for a huge sector, so a large sector, so a length at least pi, so greater than or equal to sector of angles or arguments of H bar, or arguments of tau. Okay, so everyone should be screaming at me right now because how could this be possible? I mean, it doesn't make any sense. I mean, this was a Q series which is only convergent when tau is in the upper half plane. And so if I want a pi worth of angles, I mean, it's impossible, but just this function doesn't make sense. on more than pi worth of angles, right? But what you find out is that this combination remarkably has an analytic continuation. So here, the sort of main important point is that this function, this combination, so let's say continuation and 2, okay, so let me see if I get this right. So basically we don't want this to be 0, so we want to the complex numbers, and then we remove a cut plane from -1/2. So here, so the domain looks something like, we have the complex numbers and then we have -1/2. And so what previously just made sense in the upper half plane actually has an analytic continuation across here. And so the asymptotics of this combination, in fact, on this whole this whole cut plane, as you approach infinity in any direction, will be given by this series. And you can prove that, the way that you prove that, I'll just say in words. So the proof, the idea is you write this as an explicit integral. And so then this explicit, so you write an identity that this failure of modularity is equal to some explicit integral. And that explicit integral is obviously has the analytic continuation, and also obviously has this asymptotic property. And so this is essentially how you do it. So the proof is really, you find an explicit identity to something that sort of does what you want. Okay. Yeah, so the integral looks roughly like, so I'm not going to give you the correct integral for this, because I don't know it off the top of my head, and I didn't do all the details, but it looks something like, it almost looks like a Gaussian integral. So it's given by something like x squared over 2 plus, okay, I'm integrating in x, so let me do z. Z squared over 2 plus, okay, and here it will depend. So let me give you a sort of parametric version. So let's do uz, and then over cosh z. Okay, so roughly something like this for a particular contour. So this guy is, this should be something, this is called or if you write it down correctly, is called the Borel integral. And so this Borel integral appears as the failure of modularity of something called the Appel-Lurk sums. And these modular forms, you can relate back to these Appel-Lurk sums by some identities, and then you can say, the failure of modularity I can write as something here. So you have to specialize u to some particular values. But that's essentially the integral. And so this is why you see it's not quite modular, because if I didn't have this cosh here, then this Gaussian integral, of course, I can evaluate. And that comes from the Poisson summation of theta function. And so that the fact that the Gaussian integral is something simple is related to the fact that the modular forms have these very simple asymptotics. I mean, it's essentially, that's almost how you prove it. Okay. So how am I going? I'm slowly going. Not too bad. So I need to finish maybe in 10 minutes. Was that for questions? So then I should be very quick. Okay, but so you can package this in a nice way. So okay, so I had this vector valued thing, and now I have this resummation appearing from this failure of modularity. And the way that I want to package this is some multiplicative series. So I can rewrite this thing. So I make a vector. So I make a 3-dimensional vector. So the bottom 2 rows are given by this function. And I can rewrite this transformation, or this failure of modularity, as an equality like this. So I write it as, on the top row, I just have 1s and 0s. And then I have this Borel resummation of my series. And then I have the Borel resummation of some other series associated to the second component, because up here I was just writing the first component. And then I have some constants. And I can write this in the following way. So, yes. And so writing it in this way makes it very nice because I can think of this as some kind of twisted modularity transformation. So here, this thing I want to think of as some cocycle associated to the matrix. Wait, sorry, that should have been a tau, of course. 1, 2, 1. Okay, and so this is exactly what we're going to do. So the nice property is now this matrix that I write here, I can start considering this kind of transformation property for other entries. And what you find is that it satisfies, well, it's better satisfy a cocycle condition, because otherwise, why am I calling it a cocycle? And so what you find is that if I sort of define a matrix like this in an analogous way, you find that it satisfies this property here, which is essentially a definition of it's some matrix valued cocycle property. Okay. And with this, and so here there was two properties. So we have this nice cocycle property that I just described because of this transformation. And there's also this nice analytic property that I'm erasing. And so so in general, we can sort of abstract this a little bit. And so we can define some so-called analytic cocycles. I don't know, a good name for them. So they should be some omega, which maps SL2Z into invertible matrices of some dimension, so n some integer. So here 3. And the coefficient should be in some holomorphic functions. And I'll tell you what they are in a second. So some holomorphic functions, it changes depending on the gamma. So in particular, they should satisfy, so omega of gamma should be holomorphic for tau in a given cut plane. So we take the complex numbers and we remove 1 divided by c, the reals less than minus d. Okay, and of course, if c is 0, then we just remove the whole reals. Either it's kind of natural to either remove the whole reals or just not remove anything, take the whole complex plane, but for complete generality, let's remove the reals just to be safe. And then it should satisfy the cocycle condition, and also satisfies, and I don't know how many of these I'm up to, but maybe this. Okay, so that's the definition of an analytic cocycle, and then we can define a quantum modular form of weight k with respect to a cocycle, an analytic cocycle omega, to satisfy essentially this transformation property. So we want some holomorphic function from the upper half plane, say, there's more general things. From the upper half plane, some vector valued function that's, say, holomorphic, and satisfies the transformation the modular transformation twisted by this omega here. And so, of course, I said weight k, so I should add the weight, but let me do it after. Okay, C tau plus. Okay, so a usual modular form would basically have this cocycle independent of tau. And then this cocycle condition would just turn into a representation of SL2Z. Okay, So it's easy to show that if you consider the space of these quantum modular forms with respect to one of these analytic cocycles, you can see that over usual or classical modular forms, this will be a finite dimensional space. Essentially, the dimension is just given by n. So we have n potentially new interesting functions, but then all of the others are just related to those by modular forms. Let me give myself more space. Okay. And so let me give you an interesting example of this. So if you recall these kind of Q-hypergeometric sums before, they were very, very special. In general, you would never get a modular form from this. You really need these amazing Rogers-Ramanujan identities. And you can think of that, like the analogy with the three manifolds is that most three manifolds are hyperbolic, and most quantum invariants, so all quantum invariants are written in these kind of Q-hypergeometric expressions. And so just a random one will not be modular, it will be something more interesting. And so here, if you take the function almost exactly the same, except instead of 1 here, I put a 2. Then, and here, let's make it a vector. Okay. So this was a theorem from my thesis that this is a quantum modular form with an explicit cocycle. Okay. And so this is where the link with the three manifolds come in. So in particular, I'll write down the formula, and I've been slow, so I need to be a bit terse here. So it's given by an integral version of this, in a sense. So we have e of, let's say, 2z squared tau. So this term corresponds to this here, and then we have the integral against a very special function. Okay, and there's some contour, I won't give it to you. So this thing here is called Faddeev's quantum dilogarithm. And in terms of Chern-Simons theory, this Faddeev's dilogarithm should be thought of as the path integral localized to a tetrahedra. So this example is a bit unphysical because there's no, here there would just be one tetrahedron. But these path integrals that I get at the start seemingly satisfy some kind of localization, which can be they can be reduced down to some kind of finite dimensional integrals. There's a gap. This doesn't exist in literature, so this is a gap in the physical literature. But mathematically, you can consider these integrals and you can prove that they're invariants of three manifolds. So there's no problem there. But yeah, so that's the link to the previous thing. So this should be sort of thought of as the path integral. And so let me just give you a little more detail on this guy. So this, you can write a formula when tau's in the upper half plane as follows. So this guy would be equal to some kind of multiplicative failure of modularity. Okay. So this guy has cocycle evaluated at, so if we take the cocycle associated with this matrix, it's essentially enough because we know that the generators are given by this matrix and the upper, this is one of the generators and the other was this one, which acts trivially in this case. But so this cocycle has entries given by this guy, and then here you just had some shift. So here you get some shift with Z and maybe some with the tau and some shift without. So some sort of matrix of these integrals, and the cocycle associated to this quantum modular form is given by a matrix with these coefficients. So you see that these sort of path integrals, or these, if we could make sense of these steepest descent contours and we could really evaluate this path integral, they appear as these entries in these analytic cocycles of quantum modular forms. And the reason we have not just one path integral is because there's many, in theory, for each critical point, we can take some thimbles attached to them. So we have more than just one integral. We have sort of a whole set indexed by these contours, and then we take all of them. Okay, and so then in my last seconds, I will just advertise our theorem. And so what me and Veronica showed, so it was on archive maybe a week or not even, I can't remember. So we proved that in an infinite family of examples, so this example that I just gave fits this integral. So we showed that this cocycle, let's do my 4. So these integrals are the Borel resummations of the asymptotics of these Q series. I don't know, HQ. This Q approaches 1. And so what this shows is that, and really, I mean, the modularity is by the by here. We really start with these integrals and work from there. But what it shows, combining the results, is that if you have these quantum modular forms, a large class of examples, or a large list of examples of these quantum modular forms, their cocycles are given by the resummation of their asymptotics. And so the proof here involves some very nice understanding of the steepest descent contours associated to this and how they interacted with this special function here. So you get some sort of, you apply some steepest descent, and then at each step, your contour kind of splits into many different contours, and you have to keep track of all of them. But in the end, you get a nice explicit formula, which can be written in some finite combinations of these integrals for the Borel resummation. So the proof's even constructive. But okay, let me finish there. Thanks.
Any questions? Please.
Sorry, which properties of this quantum algorithm was important for you to be able to claim that one? So what type of other function can be used?
Yeah. So this function, so the important property, sort of the let's say, I mean, we've got some upcoming work addressing sort of these more general questions, and the main important property was a theorem of Garofalidis, Kashayev. So they showed that this function is the Borel resummation of its asymptotics. So yeah, so this Faddeev logarithm, its asymptotics, the leading order is, I mean, it's a quantum logarithm, so it should have some sort of logarithm floating around, and you see the exponential of lead to what variable am I using? I'm setting tau to infinity, so I think I want it here. This guy maybe, yeah. And then a full asymptotic series. But yeah, so this asymptotic series, Stavros and Renat showed that this special function is the Borel resummation. And so to do that, one of the really important properties is that this Fadeev is actually here. This formula again only makes sense in the upper half plane as I wrote it, but it has a nice meromorphic continuation to the cut plane where you remove the negative reals. And so that's one of the other important properties.
Imagine, I think it doesn't that much difference, but imagine I give you some function that exactly has this property. So then if you have that, are you able to engineering back and get guess what this is the Borel half of something? Can you get that something from the given function with this property?
Yeah, so the kind of generalization that we're working on at the moment is, yeah, if you essentially replace this integrand by the resummation, or let's say we want, to compute the asymptotics of something like this, you can do it just formally, right? You just do perturbative, you deform to a critical point, you do formal Gaussian integration if it's non-degenerate. And so if you have a formal series in this integrand that then you want to do a formal integral of, we're working on a result which basically says that if that initial formal series is Borel summable, or it's resummable in whatever sense, then the full integral will also be resummable. And we give, again, an explicit kind of description. So at the moment, yeah, so basically the main point is that the integrand is also the resummation of its asymptotics, yeah. Mm-hmm.
More questions?
Yeah.
Explain a bit more. What does it mean geometrically to say that, the cocycle is the Borel summation of the asymptotics of the thing?
In terms of the three manifolds?
How are we supposed to interpret it? What does it mean? Is there a sort of a geometric picture behind that, or is it's just a fact that that's true? I feel I'm missing something that everybody else here has understood.
How to say?
Well, there's this fact that whatever it is, what does it actually mean that
you want, but the geometric, yeah, but I guess I want to try and understand better the geometric in terms of this integral, in terms of the three manifold that I claim it should be related to, or.
So did you expect this to be true before you had proved it?
No, so it was a long history. It's been like the last. So I couldn't give you all of the very interesting history, but yeah. So I think 10 years ago, Don Zagier was looking at asymptotics of quantum invariants, which sort of the specialization of these, should be the specialization of these infinite integrals to these discrete values in H bar. And so you can define, and what that corresponds to is setting Q to a root of unity. So it's slightly different, but okay, it's the same sort of arena. And I think there was no description physically at the time expecting, but basically he had numerical observations where he noticed that the asymptotics looked always the same, but then if you sort of shifted, so if you looked at one on asymptotics in one on n, sorry, I'm changing everything all the time, but this is an integer, and n is tending to infinity. So if n was an integer, then you got some asymptotics. But if you set n to be equal or a half integer, then you saw the same asymptotics, but there was some constant out the front that shifted. And the amazing observation at the time, 10 years ago, was that constant was exactly the original function evaluated at a half, which was this surprising modularity property. But so physically, I think there's been some progress on it. I was saying with these kind of thimble integrals, I think people have a better understanding of how it should come from the path integrals now, but it's really based on a lot of experimental observation and work. What you could expect is, so why you could expect that this function, why would you expect the quantum modularity to be related to the resummation? So I said this analytic cocycle, it had the two properties, the cocycle property and this analytic continuation. And for Borel resummation, at the very least, so for resummation, you need at least an analytic function that has some continuation, so you can take its asymptotics in some large sector. So here you have a very nice analytic function that comes essentially with the asymptotics of the original function you started with. And it's analytic on this thing. You could expect that it should be related to the resummation. That's not really a geometric answer, but I think there's still things to be understood about it. It's kind of an amazing fact, but I don't think it wasn't expected. I mean, it was really based on experiments, I would say. Yeah.
So by doing this, do you go also the Borel singularities of the story?
Where they are?
Yeah.
Yeah. So exactly. So understanding. So there's kind of two statements. There's the one, you have the quantum modularity, which says it's the cocycle is given by this, and then you say, this is equal to the Borel summation. And so the geometry of this integral dictates to you a lot about all of the singularities and everything. So in particular, you're looking at like this integral, the behavior of this integral is dictated to leading order by this dilogarithm function. So this thing here, maybe with the plus mz, okay. And so the critical values of this function give you where the singularities in Borel plane are. And the beautiful thing, of course, which is if you know a bit about three-manifold topology, to compute these Chern-Simons values at a flat connection, they're given by exactly evaluating this dilogarithm at particular numbers, which come from basically the critical point equations of this. So everything is sort of linked in together. But yeah, so it's dictated by the critical values of this, which, for an example that comes from a three-manifold, agree with the critical values of the Chern-Simons functional.
So you get some invariance related to this?
Yeah, exactly. Yeah, exactly. So I mean, so last year, so there was a definition a long time ago, which was conjectured to be the asymptotics of a well-known quantum invariant. But no one can prove that conjecture. It's this famous volume conjecture, or even stronger version of it. But you can define a series that you conjecture is the asymptotics. And then that was defined 10 years ago. Last year, we proved that it is an invariant of the three-manifold. So you have this series asymptotically as an invariant. And then if you can compute its Stokes constants, then as a byproduct, it's also an invariant. But again, there's lots of conjectures in this area, but one of the conjectures is that if you put all of these Stokes constants into a big generating function, this should be given by the 3D index associated to this thing. So this is related to some BPS counts in some, compactification of blah, 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 this magical 6D superconformal field theory that I don't understand, but apparently I should. But yeah, so there's a nice relation there, but that's just conjectural. So I think with our results, we might be able to prove it in examples, but we haven't even done that yet. So, okay.
Okay, so I think I propose to keep the discussion in the non-copyright and over there, but also for someone that wants, we want to actually take a picture of that to feel like the idea. So I'm just the ambassador, and so if we want, then we can just gather outside and take a picture to keep it in a memory.